Hi guys, we're going to be looking now at how to do a sophisticated process with chi-squared, meaning that we're going to show all of our work out and show you how this is done. In order to set up our observed frequencies, we should set up some intervals. And in this situation, I want to know whether gender and let's say skull circumference, I want to know whether these are independent factors. If they're independent, well then it would make no difference whether you're male or female in terms of the likelihood of you having a big skull or a small skull. If, however, they were dependent, well then males might be more likely to have small or large skulls, whatever the case may be. And let's have a look to see how that's going to work. And so I'm going to set up then my observed frequencies. Here I've got my genders, and we'll go with male and, oops, maybe I'll bring it down one more column, male versus female. And now I need to look at my skull circumferences. And so I know that my skull circumferences range from the high 50s, about 58, up to the low 70s, about 72. So why don't I set them up in intervals of, say, from 58 up to 60, let's try 62. And then we'll go from, say, 63 up to 67. And we'll go from 68 up to 72. And certainly my formatting leaves a lot to be desired. Perhaps I can merge and center that one. And perhaps I should, in fact, center everything. Yeah, it's a bit better. Alright, I've got to work out how many males there are who have got skulls between 58 and 72. It's going to be a lot easier if I reorder my data. So let me select all of my data and, oops, and go up to data, and I want to, where is, oh I see, sorry, up here, data. Let's sort it. I want to sort by the gender, and I'll sort on values in order from, doesn't really matter I suppose, and let's also then sort by the skull circumference, and smallest to largest, that looks okay, so we'll say okay. And let's rearrange everything. Now I had to select all of the data first so that all of the corresponding cells moved as well. Looks like I've got, let's see, females. 1, 2, 3, 4, 5, 6, 7, 8, 9 females who have got between 58 and 62 centimeter skulls. Continue with my females. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. And then between 68 and 72, I've got only 2. Let's move on to the males. From 58 to 62, I've got just 2 of them. From 63 to 67, 1, 2, 3, 4, 5, 6, 7, 8. And from 68 to 72, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, now I know what you must be thinking, that yes, we do have values here that are less than 5. But let's just see what happens with my expected frequencies. Remember, these are the observed frequencies. Perhaps I don't want that one to be centered. Now, I'll just finish this off. So I know that I've got my sums at the far right. So that's going to be equal to the sum of these 3 cells. And I'll copy that down. And look at that, 20 males, 20 females. Let's center that information. And then here we've got the sum of the values above and center. And in fact, I can drag this across. I can drag this value across in order to calculate the other amounts. Let me just put all of these into bold so that we can see that they are sums. Probably a good idea for me to do that with all of my other subtitles. And in fact, I tell you what, I'm going to see if I can format this particular cell. How do I do that? Format cells, alignment, and maybe I'll bring my text up like that, pretty flash. And perhaps I need to merge these two cells and redesignate that one. Well, alright, you can see this is not perfect. Maybe I should merge all three of these. See if that helps. There we go. Better? And maybe these are the sums, center. And perhaps these are the sums. Good. And we're just about ready to go, I think. Perhaps I should just get my borders in. Alright, not too bad. I think I'll just merge these ones and set my alignment up so that it's in the center. And yeah, I think that looks pretty good. I'm pleased. So why don't I take all of this stuff and copy it down. So I've got the, come on, copy and paste. Oops, there we go. And I'm going to change this one to expected frequencies. And that's where all of these cells are going to change. So let's get rid of these for the time being. So this cell is going to be equal to the, remember it corresponds to this one, it's going to be equal to the product of this cell times this cell. So that's going to be equal to that cell times that cell, and then we'll divide that result by the contents of the supersum down there. And I'll do this each time. It's going to be this one times that one divided by that one. And this one's going to be equal to this one times that one divided by that one. And once again, I can figure out what the sum of these amounts is. No surprise, there's still a total of 20 males. And you'll see that my problem with my expected value being less than 5, my observed value being less than 5, it's no problem, because my expected value is safely above 5. Let's do the same thing with the females. So female sum of the rows times the sum of the columns divided by the supersum equals sum of the row times the sum of the columns divided by the supersum. And lastly, this is equal to the sum of the row times the sum of the column divided by the supersum. And good, once again, all of my expected frequencies are above 5. Let's stick in the overall sums, copy them across, And you see that once again I've still got 11 people whose skull circumferences are in the smallest interval, 17 and 12, same supersum, and those are my expected frequencies. Now, if I was to copy these into Word, I'm not going to get full credit. Yeah, I'll work with that chi-squared in a minute. I'm not going to get full credit as this being a sophisticated process, because in Word I would actually need to show what my calculations were in order to obtain these expected frequencies. So maybe I should, whoops, perhaps I can take this, this one, put it in again, and maybe at this stage I should insert the formulas that demonstrate what was going on. And so, of course, I've got a fraction, and in that fraction it's going to have 20 times, I've got to go back to my math symbols, where's my times, there it is, 20 times 11 divided by 40. And, well, you get the idea. I don't know if I've really got the energy to do them all. Might be quicker, there's always a trick, to copy in the fractions. I'll replace their values in a minute. You'll see that I'm not going to need to replace all of them, which is going to be convenient. And I know that I can be a bit obsessed with formatting, but why don't we just make sure that everything is aligned. Cell alignment, align, center. Lovely. And now I just have to go through and change some of these numbers. So this one should have been 20 times 17. This one should have been 20 times 12. This one should have, oh, it doesn't change. Should be 20 times 17 and 20 times 12. You might notice in this particular example, because I have an equal number of males and females, in a totally random situation, supposing that it was completely independent, that's why your expected values would be the same. Our distribution of the 40 skulls, we would expect there, if there's an equal number of males and females, for there to be an equal number of males and females in each of the 3 different intervals of skull circumferences. So no real surprise that they came out to be the same. There we go, now I've shown where the values in the expected frequencies table comes from. Let's go back to Excel so that we can start calculating chi-squared by hand. I need to set up a series of columns, and so first let's make our observed frequencies. I don't know how to do subscript, so I'm going to update these columns when these column headings when I go into Microsoft Word. These are my expected frequencies. Let's now find the difference between the observed minus the expected. Next, let's take this previous value, observed minus expected, and square it. And lastly, we need to do the observed minus the expected all squared, the previous column, and then divide the overall result by the expected values. And those are my column headings. Underneath the observed values, I'm going to put them all in. I'm just going to read them across 2, 8, 10, 9, 9, 2. The expected ones, I've got 5.5. So I'm reading the corresponding cells, 5.5, 8.56, 5.5, 8.56, all of them above 5, lovely. So this is going to be a valid chi-squared test. The observed minus the expected values. So I need to take this cell and subtract the contents of this cell, and then I'll drag it down in order to copy all the corresponding values. Now I need to take the square of the previous cell, so G15 to the power of 2, and copy it down. Now I need to take all of the values that I just had, FO minus FE all squared, and divide them by the expected frequency cell. Oops, sorry. Need to divide by that cell. There it is. Let's drag that down to copy them all. And at the very bottom, we're going to take the sum of all of these amounts. Okay. So let's put in our borders. And this one maybe should be bold because it's the sum of the whole thing. You can even say equals my chi. I'm a bit nervous about that. It's going to think it's a formula. Never mind, let me leave it like that. I'll just stick a border around it to show it's a part of the table. And probably doesn't hurt to center everything. Okay. Let me copy this entire table over into my Microsoft Word document. Okay. Now's a good time for me to change these with some better notation. So I want to show that these are the observed frequencies. I'll replace them with a formula. Insert the equation f, oops, perhaps I better tell them I'm doing a script with a subscript. So that's going to be an f sub o for the observed values, and this is going to be, well, really the same thing. Let's just copy it over and then just change my e. Come on. It's temperamental, isn't it? All I want is, there we are, that. So, sorry about the tedium of you having to watch me enter formulas. I imagine you're much quicker at this than I am. So, let's insert another equation formed out of FO minus FE, wasn't it? So, script. O minus F as a script, so it's followed by an E. Alright, let's take this amount as the new heading for the next column, and then stick it into some parentheses, and then raise the entire amount to the power of 2. And lastly, we'll take the contents of this column heading, copy it into the last column heading, and then we'll highlight everything, select the fraction, and put it over the script of f. F script subscript of E. Okay, maybe I should reformat these cells a bit. Alignment, dead center, much nicer. And so there's your chi-squared table, justifying that you've got 9.846. Now then, the degrees of freedom in this particular example is we take the number of rows, which is 2, and so I should really put this formula in somewhere. Let's insert another formula. The degree of freedom will be equal to the number of rows, which is 2, times the number of columns, and that, of course, you can see pretty quickly, is going to give you a degree of freedom of 2. Alright, we're going to have to look up on the chi-squared table now. I'm afraid I don't have a copy handy with me, but so you have to forgive me, but I'm just going to figure out what my table value is. And oh yeah, I probably should have shown somewhere that my overall chi-squared is calculated by taking the sum of all of these elements. So I'm going to move this formula here back up to there. And oops, I left out the chi-squared at the beginning. So you can find chi-squared by going all the way over to the far right. And there it is, chi. And we'll highlight in order to create the superscript, the exponent of 2, and then equal to that amount. So there's the formula. And it's sufficient now you've shown the formula and the work below in order to work out that chi-squared is going to be 9.847 if I round to 3 decimal places. So I'm just going to get rid of some stuff up at the top that I don't need anymore. So this is all going to fit nicely on one page. Okay. So we'll bring this one down. And of course we can now replace this with equals 9.847. And in order to show that this is the calculated value of chi-squared, let's create another subscript. And we'll call it the calculated value of chi-squared, 9.847. Now something I forgot to do at the beginning of this whole process is to define my null and my alternative hypothesis. So, h0, I'll do this with an equation, h sub 0 is, can't remember how they word it exactly in the book, but is the, what is it? The are independent factors, and the alternative hypothesis then, just have to update it, say are not independent factors. Your alternative hypothesis then involves, oh come on, why does it do this? There we go, h1, the alternative hypothesis. Great. Now I've defined my hypotheses. I'm ready to actually perform the chi-squared test. And so I'm going to compare my calculated chi-squared value to the chi-squared value that appears on the table. Usually we look at a 5% significance level. And so in that case you're going to need to go to the column that is labeled with a 0.95. I'm actually kind of want to do this properly. So let me see if I can quickly find a chi-squared table. Chi-squared table. Oh, this looks even better. We'll just take one of them and hope that it's big enough to see. Yes, of course it would be slow. Alright, don't know if you can see this, but when we got degrees of freedom, oh, no, this is only giving us a 1%. Yeah, sorry. We're going to need to try going back to maybe this one. Ah, yes, that's what I'm looking for. Why is it showing? I don't want degrees of freedom as high as 21. Perhaps I can go back and see if I can find the ones for a degree of freedom at 2. Yes, that's it. Okay, on this particular table, this is different from our IB package table. On the IB package table, you need to look in the 0.95 column. This one, for whatever reason, we need to look in the 0.05. And so for degrees of freedom at 2, with a 5% significance level, my critical value of chi-squared is 5.991. So we go to Word, critical value of chi-squared. It's 5.991. Now you can see that our value of chi-squared is significantly higher than 5.991. I'm always lazy about doing this kind of thing, and I just like to copy it. Ooh, go on. Frustrating. Sorry, I know this is probably awful to watch. Alright, the critical value of chi-squared at a 5% significance level for 2 degrees of freedom is seen to be, forgotten it, 5.991. Since the calculated value of chi-squared is greater than the critical value of chi-squared, we reject the null hypothesis of H0 . And this means that gender and skull circumference are not independent factors. And this probably shouldn't be a big surprise to you if you look at our original table. I mean, when we look at this, it's fairly apparent that males, according to this information, have got larger skull circumferences, and very few of them have got small ones, while with females it's just the reverse. And it's such a significant departure from what we expected. When we compare what we would have expected to see compared to what we actually did see, it's such a significant departure that our chi-squared value ended up being bigger than what the table says is the maximum allowable departure for them still to be considered independent. And so because our calculated chi-squared value is larger than the maximum value, we have to throw out the hypothesis that they are independent and say, we reject it, they are not independent factors. And that's how to do a chi-squared test by hand.